my name is Aryani Azamparas from the University of Melbourne, and I would like to present our work DDB Diffusion-Driven Balancing to address spurious correlations. To explain spurious correlations, let's consider the waterbirds dataset. The task is to classify images into land birds and water birds. However, most land birds in this dataset appear on land background, and most water birds appear on water background. This creates a correlation between background and label that is not truly causal. ERM models, those trained with empirical risk minimization, tend to exploit such shortcuts. They rely on correlated features rather than causal ones, which reduces generalization when the correlation breaks. From a compositional perspective, each image has two components. Causal part, which determines the true label. For example, in waterbirds dataset, the part of the image which contains the bird is the causal part, and the spurious part correlates with the label, but it's not stable across domains, which is the background in our example. We further formalize the problem using group annotations. Majority group samples, which have the combination of causal and spurious parts which dominates in the training set. For example, here waterbirds on water background and land birds on land background, and minority group samples which have the rare combination that breaks the spurious correlations. For example, waterbird on land background and land birds on water background. ERM models perform much worse on minority groups, and our objective is to maximize worst group accuracy. DDB addresses spurious correlations by generating minority group samples to balance the dataset. We leverage the Stable Diffusion, a state-of-the-art energy generative model. Given a majority group sample, our method edits the causal part to create a corresponding minority sample. For example, starting from a water bird on a water background, we can edit the bird to make it a land bird on the same water background, thus producing a minority sample. To control this process, we use textual inversion and segmentation along with the filtering method to remove low-quality samples. The first step is learning causal features. We apply textual inversion to learn spatial tokens that represent the causal features of each class. By fine-tuning the text encoder of the diffusion model on a few examples per class, the model learns to reconstruct those images using the new tokens. The next step is altering the causal part. We use a Stable Diffusion inpainting model to alter only the causal region. A segmentation tool provides the mask, and noise is added only to the masked area. The image is then denoised using the learned tokens via textual immersion. For example, a land bird on land can be transformed to a water bird on land, producing a valid minority group sample. Sometimes, generation fails due to poor segmentation or diffusion artifact. To filter such cases, we use the intuition that if the causal part has been correctly changed, the ERM model should assign higher probability to the new class. We therefore define two thresholds: ERM attribution score on the causal region and ERM softmax score on the new image. Only images passing both thresholds are retained. Finally, we augment the dataset with these filtered samples and retrain the ERM model on the generated ones and the initial samples. After retraining on the balanced dataset, we consistently improve worst group accuracy across 3 benchmarks. On waterbird and metashift, our method outperforms other state-of-the-art approach to mitigate spurious correlations too. We introduced DDB, a framework to mitigate spurious correlation. We control the diffusion process with textual inversion, segmentation, and inpainting model. And we introduce the filtering strategy to ensure that just high-quality generated samples are retained. Thank you for your time and watching this video. Please send me an email if you have any questions.